This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on integration by parts. The formula is the integral of u dv equals uv minus the integral of v du. And the challenge is to determine which is going to be u and which is going to be dv. So let's look at an example. We have the integral of 2x natural log 3x dx. U is the part that is easy to differentiate. Take the derivative. Now, frankly, 2x is easy to differentiate. Natural log 3x is easy to differentiate. So that doesn't really tell us much. dv is the part that is easy to integrate. Now, 2x is certainly easy to integrate, although it does make it more complicated. The integral of 2x is x squared. And usually that's not something we want. But natural log of 3x is not something we can integrate directly. So the natural log 3x is going to be u, and the dv part here is going to be 2x dx. Once we're here, we have to go ahead and find out what du is, and we have to find out what v is. To find du, we're going to take the derivative with respect to x of both sides. So the derivative with respect to x of u is the derivative with respect to x of the natural log of 3x. Derivative with respect to x of u is du dx. The derivative of the log of 3x is 1 over 3x times the derivative of 3x, which of course is 3. So we get du dx is 1 over 3x times 3 thanks to the chain rule. And 3 divided by 3x, of course, is just 1 over x. And we need du, so multiplying both sides by dx, we're going to say that du is 1 over x dx. So we have du. Now, dv is 2x dx. We need to get v. We will do that by integrating both sides. So the integral of dv is the integral of 2x dx. Integral of dv is v. Integral of 2x dx is x squared. So we have u, dv, du, and v. We have everything that we need to set the problem up using integration by parts. Our formula is the integral of u dv is uv minus the integral of v du. Integral of u dv, natural log 3x times 2x dx, equals uv, natural log 3x times x squared, minus the integral of v du, x squared times 1 over x dx, which you can see. Again, uv, I changed the order. Instead of writing log 3x times x squared, I'm writing x squared times natural log 3x, minus the integral of v du. Again, x squared is v, and du is 1 over x dx. Notice that this reduces nicely, and we're almost finished with the problem. X squared times 1 over x is just x, and then the integral of x is x squared over 2 plus c. And that finishes that problem. So again, the process requires you to identify what is u, what is dv, find du and v, and then plug it into the formula to find the solution. Our next example is the integral of the arc sine of x dx. What is u? What is dv? Well, I want to integrate arc sine of x, so we certainly wouldn't make that dv. There'd be no u to use. So here u is going to be inverse sine of x, and dv is going to be dx. Our goal is to find du and v. To find du, we're going to take the derivative with respect to x of both sides. Derivative with respect to x of u is the derivative with respect to x of arc sine of x. d dx of u is, of course, du dx. The derivative of the inverse sine is 1 divided by the square root of 1 minus x squared. We need du for integration by parts. Multiply both sides by dx, and we get du is dx divided by square root of 1 minus x squared. That looks pretty complicated. But over on this side, the integral of dv is the integral of dx, and v equals x. We know our formula is the integral of u dv, arc sine of x dx, is uv, arc sine of x times x, minus the integral of v du, vx du dx, over root 1 minus x squared. So how are we going to do that? uv, arc sine of x times x, I'm writing as x times arc sine of x just because it's a little nicer to look at. Minus the integral of v du, v times du, how about x divided by root 1 minus x squared dx. This integral can be solved using U-substitution. If u is 1 minus x squared, his derivative of negative 2x is sort of in the numerator. If the numerator is a multiple of the derivative of u, then you have a chance for U-substitution to work. So here we have the integral of the inverse sine of x is x times the inverse sine of x minus the integral of x divided by the square root of 1 minus x squared. I'm choosing to use w since I used u before. That would make sense. We want to go ahead and do this integral using w substitution. The derivative with respect to x of w is the derivative with respect to x of 1 minus x squared. So dw dx is negative 2x. And for u substitution, w substitution, I want to solve for dx. So dw is negative 2x dx. dw divided by negative 2x equals dx. So we're going to replace this integral of x over root w times dw over negative 2x. You'll notice the x's cancel. Now let's think about this negative 2 downstairs. That's really 1 over negative 2. But with this minus sign in front, if I pull out negative 1/2 and I multiply it by negative 1, that will give me positive 1/2. The x's cancel, and I'm just left with 1 over root w dw. Root w is w to the 1/2. This whole piece then is the integral of w to the negative 1/2 dw. Now we have to use the power rule, increase the exponent by 1. So that would be w to the negative 1/2 plus 1 over negative 1/2 plus 1. But negative 1/2 plus 1 is 1/2. So this integral is w to the 1/2 over 1/2. What's nice about that is this 1/2 and that 1/2 will divide out, and I get x inverse sine of x plus w to the 1/2 plus c. W to the 1/2 is the square root of w. And what is w? W is 1 minus x squared. So let's finish this by saying x times the inverse sine of x plus the square root of 1 minus x squared plus c. That will be our integral of the inverse sine of x dx. Our next question is a definite integral, the integral from 0 to pi over 3 of x times sine x dx. Now there's a few ways you could do this. I prefer, in the case of integration by parts, to ignore the endpoints until the end of the problem. So rather than doing this, I'm going to simply do the integral of x sine x dx. And then once I get the antiderivative, I'll plug in the endpoints and subtract. So I need to figure out u and dv. U is the easy thing to differentiate. dv is the easy thing to integrate. Well, they're both easy to integrate and differentiate. But if I integrate x, I get x squared over 2. That makes it more complicated. So in this problem, u should be x and dv should be sine x dx. Same process, we need to get du and v. If u is x, take the derivative with respect to x of both sides. Derivative with respect to x of u is the derivative with respect to x of x. So du dx is 1, which means du is dx. Very nice. Over on this side, the integral of dv is the integral of sine x dx. Integral of dv is v. Integral of sine x is minus cos. Remember, derivative of sine is cos. Derivative of cos is minus sine. So the derivative of negative cos would be sine. Integral of sine minus cos. So v is minus cos x. We have u, du, dv, and v. We have everything we need to do this integral using integration by parts. Our formula, integral of u dv, is uv minus the integral of v du. uv, x times negative cos x, minus the integral of v du, minus negative integral of negative cos x dx. And that's what we're working on. Remember, eventually we're going to need to plug in the endpoints of 0 and pi over 3 and subtract. But this is what we're working with, and we're almost finished. Rewriting it this way, integral of x sine x dx is negative x cos x minus the integral of negative cos x. Certainly that minus can come out. That'll become plus the integral of cos x. The derivative of sine x is cos x, so the integral of cos x is sine x. And we should put in a plus c in the case of an integral without endpoints. But we have a definite integral. We want to evaluate this at some endpoints. So we're going to ignore the c and evaluate the antiderivative at the endpoints and subtract. So the integral from 0 to pi over 3 of this function, take our antiderivative, negative x cos x plus sine x, evaluated as x goes from 0 to pi over 3. It'll give me negative pi over 3 cos pi over 3 plus sine pi over 3 minus quantity negative 0 cos 0 plus sine 0. So we see that with our fundamental theorem of calculus. Cos of 0 is 1, negative 0 times 1 is 0, plus sine 0 is 0. This whole piece just becomes 0. Cosine of pi over 3 is a half. Sine of pi over 3 is root 3 over 2. So we get negative pi over 3 times a half plus root 3 over 2 minus 0. So negative pi over 6 plus root 3 over 2 will be the answer to that question. We have one more to look at in this lesson, and that is the integral of e to the x cos x dx. Here, they're both easy to integrate, they are both easy to differentiate, and frankly, either strategy works. I'm going to choose to use u as e to the x and dv as cos x dx. If you did it the other way, though, you still can get the correct answer. Let's go through our process. We need to find du and we need to find v. The derivative with respect to x of u is the derivative with respect to x of e to the x. So du dx is e to the x, multiplying both sides by dx. Du is e to the x dx. Over on this side, the integral of dv is the integral of cos x, so v equals sine x. We have u, du, dv, and v. Now we are ready to use integration by parts. So the integral of u dv, integral of e to the x cos x dx, is uv e to the x sine x, minus the integral of v du, minus the integral of sine x times e to the x dx. Okay, so clearly we're not finished yet, and I'm just going to rewrite this last piece as the integral of e to the x sine x dx. What I have to do is I have to do integration by parts again with this piece of the problem. So here's where we are. We need a u and a dv here, and I need to be consistent. I let u be e to the x the first time. I need to let u be e to the x the second time as well for this to work. I'm going to use capital U and capital V here. So capital U is e to the x, d capital V is sine x dx. Again, I need to get d capital U and I need to get capital V. The derivative with respect to x of u is the derivative with respect to x of e to the x. So du dx is e to the x, du is e to the x dx, again, for this piece. Over here, the integral of dv is the integral of sine x dx. The integral of sine x is minus cos, so we get capital V is minus cos x. Our goal is to do this integral. So at this point, we are ready to go ahead and use our integration by parts formula, which is integral of u dv is uv minus the integral of v du. So the integral of e to the x sine x dx is uv e to the x negative cos x minus the integral of v du minus the integral of negative cos x e to the x dx. That's what that looks like. I want to clean that up, and then I want to plug it in up here for the integral of e to the x sine x dx. So again, this is where we are, and this is what I saw on the previous page in terms of what this looks like. And let's simplify this. That's negative e to the x cos x plus the integral of e to the x cos x dx. And now I want to plug all this in parentheses for this part up here. So I'm going to have the integral of e to the x cos x dx equals e to the x sine x minus parentheses negative e to the x cos x plus the integral of e to the x cos x dx. So again, this is what we have up here. Plugging that thing in big brackets. Now you can see I have the integral of e to the x cos x dx equals all of this. My next move is to distribute this minus sign. It'll become plus e to the x cos x minus the integral of e to the x cos x dx. Again, notice minus negative becomes plus e to the x cos x minus plus minus the integral of e to the x cos x dx. But notice, integral of e to the x cos x dx on this side, e to the x cos x dx on this side. Let's add the integral of e to the x cos dx to both sides. On the left side, I'm going to get twice the integral of e to the x cos x dx. On the right side, those cancel out, and I just have e to the x sine x plus e to the x cos x. And then divide both sides by 2, and don't forget to put a plus c at the end, and that is our final answer to that challenging question. The required integration by parts twice, and then adding the integral to both sides of the equation to get the solution. And that will conclude this lesson.